Hi viewers, welcome to all. Here we are discussing about a project to efficient approximate unsigned multiplier by developing new configurations for approximate 4:2 compressor. Electroencephalogram is a form of cardiovascular measurement and dynamic information from the brain conditions. However, the numerous noise usually harm the amplitude and time period of the signal from the EEG signals at the following a transitions of the analog EEG signal from the sensor modules into a digital format. The appropriate digital filters may be used to remove different forms of noise such as baseline wander, power line interference, and high frequency noises and psychological artifacts. This proposed work would implement a one-norm minimizations in the FIR filter with a linear step method to minimize the sparse complexity and reduce the minimax approximations errors for sparse maximization. This proposed work of the digital filters, which developed using two different approximate computing multiplier to reducing power consumptions and design complexity. So given this fact, the several rules of selecting indicators of potential zero coefficient to be used in one standard optimizations are adopted in the proposed algorithms. The efficacy of the proposed designs algorithms was developed in Verilog HDL, simulated and synthesized in Vado Zinc FPGA, and finally proved all the parameters in terms of area, delay, and power. Now we can verify the base papers. So this base papers, they are fully focused for approximate computing architecture of 4:2 compressor used unsigned multipliers. Okay, so here they are given so different number of 4:2 compressors. Okay, so here the first one figure, it will be showing the exact method, that means the traditional method of 4:2 compressors. It will be designed with the two full adder. Okay, so each full adders contains the two half adders. Okay, so one full adder is having a 5 logic gates totally. Okay, so two full adders means this 4:2 compressor will occupy 10 logic gates. Okay, so based upon this 10 logic gate, it will take number of LUTs in the FPGA design. Okay, so here the background architectures, they are given as sum, carry, and cout operations, and additionally they are given the number of compressors operations. Here you can check it. Okay, so 3 and 4 different approximate computing method they are used. The first one is the approximate compressors with a 6 gate. Okay, AC6G approximate compressor free gate 1. Okay, and third one is approximate compressor free gate 2, and fourth one is a AC 6G approximate compressor 6 gate designs. Okay, so based upon this design configurations, okay, they will give us sum generations and carry generations based table. Okay, so here you can check the table 2 ACF6G compressors. Okay, so it's having 1 to 16 different designs it will be have. Okay, the sum generations and carry generations equations they are given, and example architectures they are given in figure 5. Okay, so AC6G12. Okay, so here it will take totally 16 different architectures. Okay, and here you can check the table 4. Okay, so this one is a ACFG 2 1. Okay, 1 to 12 different architectures. Okay, so this ACFG 1 2 and ACFG 1. Okay, so here the table 3 and table 4, you can check the sum value and carry value. Here they are given as a sum will be 1 only and carry will be x1, x2, x3, x4 only. Okay, so they are not put it for any other equations here. Okay, they are taken as a constant x1, x2, x3, x4 values. Okay, that is an input, right? So that input will directly called as a output. Okay, so that is a concept of this paper to reduce the number of logic gate in the compressors part. Okay, so how they are reduced this logic gates means they are used as a K-map technique. Okay, so here the figure 6 also they will shown right. Okay, so based upon this sum and carry equation. Okay, so here they are given right table 2. Okay, so this sum and carry equations we can possible to design a K-map table. Okay, that K-map table based upon number of ones and zeros. Okay, we can develop this type of x1, x2, x3, x4 output. Okay, the constant output we can possible to take. Okay, so here the figure 7 shows the came up of ACFG to 1. Okay, the sum output given in a first one and carry output given in a second one. Okay, so based upon this number of configurations, we can develop the proposed multiplier. Two different technique it will be applicable. So here this figure 2 it will be showing ACFG22. Okay, so and the figure 9 it will be showing ACFGI. Okay, so here what is the different means, so this compressors is a different part. Okay, so ACFGI and AC6G. Okay, and ACFGII and AC6G. Okay, so this compressors only different, other technique will be same. Okay, so this is a final addition part. Okay, so based upon this multiplier generations, we will develop the two different multipliers. Okay, the proposed multiplier 1 and proposed multiplier 2. After this proposed multiplications, we need some application to prove this concept. Okay, so that's why we are used the FR filter. Okay, so now we can verify the Verilog HDL coding for this ACFG1 and ACFG2 of the proposed multipliers. Okay, so this is a test bench of the coding. Okay, so here the verification part and the error distance will be calculated here. Okay, so that is a original value and the error value. Okay, so this is a multiplication stop model. So this multiplication simulation we are given here. Okay, so here A input, B input, and this is a data check original value, and this is the error distance, and this is a proposed output. Okay, product output. Okay, so here you can verify the error distance and the input and output of the any values. Okay, you can check the error value and the proposed value. Okay, so based upon this configuration, the proposed work will be developed as a FR filter design. Okay, so this is a FR filter architectures. Okay, so this is low pass FR filters. So here we are given as a EEG signal. Okay, so that simulation output will be given here. Okay, so this is a EEG modulation signal. Okay, so same like as a seashore detection signal. Okay, so here you can check the signals, input signals and the filter output. Okay, so the filter output reduces the noises and it will highlight the peak value of the input signal. Okay, so and this work will be synthesized in Xilinx Vertex 5 FPGA. Okay, so here this is a multiplications synthesis report. Okay, so number of LUTs and number of occupied slices, number of IO bits. Okay, and here this is a RTL schematic for this architecture's multiplier. Okay, so here this one is for AC6G method. Okay, so instead of this one AC61 only we called. Okay, and instead of this ACFGI. Okay, so ACFGI1 only we called. Okay, this ACFGI and AC6G and ACFGI2 will be customizable. Okay, so you can, which one you are needed, you can command it and uncommand it. Okay, so if you need 16 or 15, 12, okay, which one you are needed, so we will put the codings in the folder. Okay, you can check all the comparisons value. Okay, whatever you are needed. Okay, so you can synthesize it and you can take the results. Okay, so it's not a biggest trouble. Okay, just command it and you can take the comparisons. Okay, so here the FR filter also same. Okay, so here you can check the design summary of number of slice registers, number of occupied slices, LUTs. Okay, and IO base. Okay, and you can check the delay. Okay, so 3.103 nanoseconds, and you can check the RTL schematic. Okay, so here we are choose only two comparisons for proposed multiplier 1 and proposed multiplier 2. Okay, so that is taken from AC 6G1 and AC FGI 1. Okay, so this one comparisons only we are taken. So as per the requirement, okay, so if we need, we can possible to take okay, the number of comparisons. Okay, so the comparisons of FR filter design also taken the single comparisons with a 2 multiplier design. Okay, so you can check the comparisons analysis chart and parameters. Okay, now we can verify the abstract document of this project. Okay, title, base paper abstract, enhancement of this project, proposed title, proposed abstract, existing system. Okay, disadvantages, proposed systems. Okay, and related notes for all the designs. Okay, and finally literature survey and references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.